All right, let's dive into one of the most fundamental circuits in all of electronics. It's so simple, so elegant, and believe me, it is working all around you right now, in ways you probably don't even realize. Have you ever been listening to a great sound system and just wondered, how does it do that? How does it send those deep, booming bass notes to that big woofer, but at the same time, send the sharp, high-pitched cymbal crashes to that tiny little tweeter? It kind of seems like magic, right? Well, it's not.
The secret is actually this tiny, incredibly clever circuit that acts just like a bouncer at a really exclusive club. It's got a super strict door policy, and its entire job is to control which electronic signals get in and which ones don't.
And this electronic bouncer, this gatekeeper, it really only has one simple rule. It only lets the lows in. Now, in the world of electronics, lows just means low-frequency signals. Anything else, any high-frequency signals, they get turned away right at the door.
So let's look at this bouncer's job description. It's pretty straightforward. First, it passes the low-frequency signals, no problem. Second, it blocks, or the technical term is attenuates, the high-frequency ones. Third, it's passive, which is a fancy way of saying it doesn't need its own battery or power cord to work. It just does its job. And finally, it never boosts the signal. The output is always going to be a little bit weaker than the input. No exception.
So how does this amazing little filter actually do its job? Well, it's not just one thing. It's a two-part team. And get this, all it takes are two of the most basic electronic parts you can possibly find, a resistor and a capacitor. Okay, so let's meet the team. First up, we have the resistor, which we'll call R. Think of it like a simple hallway. Its opposition to the signal, its resistance, is always the same. It never changes. But the capacitor, C, well, that's the real star of the show. That's our smart bouncer. Its opposition, which we call reactance, isn't fixed at all. It actually changes depending on the frequency of the signal that's trying to get through. And that right there, that's the key to everything.
So how does our smart bouncer, the capacitor, actually decide who gets in? Well, it follows a very specific rulebook, and that rulebook is based entirely on one thing: signal frequency.
And here is the golden rule, the core principle. The reactance of a capacitor varies inversely with frequency. That sounds complicated, but it's not, I promise. All it means is that as the signal's frequency goes up, the capacitor's opposition to it goes down. And if the frequency goes down, its opposition goes up. It's a simple inverse relationship, and it's the secret sauce for this whole filter. So let's picture this. A low-frequency signal, like a deep bass note, comes up to the gate. The capacitor sees it and acts like a brick wall. Its opposition is super high. So the signal just says, okay, can't go that way, and it has no choice but to continue right along the main path, straight to the output. It gets in, no questions asked.
But what happens when a high-frequency signal, like a cymbal crash, shows up? Well, for high frequencies, the capacitor's opposition just drops to almost nothing. It basically opens up a side door, a super easy shortcut to ground, and the signal, being lazy, always takes the path of least resistance. So it zips down that shortcut and gets diverted away from the output entirely. It's been bounced.
Okay, so we get it. Low frequencies pass, high frequencies get blocked. But where exactly is that line? I mean, every good bouncer has to have a clear official door policy, right? This graph here shows that policy perfectly. It's what we call a frequency response curve. On the left, you've got the pass zone, where all the low-frequency signals are cruising right on through. And on the right, you've got the stop zone, where the high-frequency signals get blocked. The most important part of this whole thing is that little slope in the middle, that transition point between the two zones.
And that specific point has a name. It's called the cutoff frequency. This is the exact frequency where the constant opposition from our buddy the resistor is perfectly matched by the changing opposition from our bouncer, the capacitor. It's the precise moment the filter really starts to kick in and do its job.
You'll also hear this cutoff frequency called the -3 dB point. Now decibels, or dB, that's just a technical way to measure signal power. Don't get bogged down by it. All you really need to know is that at this -3 dB point, the output signal's power has been cut exactly in half. Its voltage has dropped to about 70% of what it came in as. This is the official point where the blocking really begins.
So how do you actually set this cutoff point? Well, you use this simple formula. But I want you to think of it less like scary math and more like a recipe. You get to choose the ingredients, the values for your resistor R and your capacitor C, and by picking the right ones, you can tune your filter to let in exactly the range of frequencies that you want. Pretty cool, huh?
Now, what if one bouncer isn't quite enough? What if some of those pesky high frequencies are still sneaking past the velvet rope, and you need an even stricter door policy. Well, it's simple. You just hire more bouncers.
A standard filter with just one resistor capacitor team is called a first-order filter. It has what's called a roll-off slope of -20 dB per decade. That just means it gets pretty tough on high frequencies. But if you connect two of these filters one after another, you create a second-order filter. Now you've got two bouncers at the door. And this new setup has a much steeper -40 dB slope, which makes it way more aggressive at blocking those unwanted high frequencies.
But of course, there's always a trade-off. The pro is obvious. That steeper slope is way better at getting rid of the signals you don't want. But the con? As you add more stages, you get more signal loss, more attenuation, right there at the cutoff frequency. So even some of the signals you do want to keep get a little bit weaker. It's a balancing act.
So where will you find our little electronic bouncer working? Oh, just about everywhere. We're talking audio speaker systems, just like we started with, directing all that bass to the woofers. They're in the power supply for your laptop, smoothing out the electricity. They're used in radios to tune into a specific station. And they're in audio amplifiers, acting as a treble cut or hiss filter, getting rid of all that annoying high-frequency noise.
So there you have it, the passive low-pass filter. It's the perfect example of how a really simple idea, using just two of the most basic parts imaginable, can become an absolutely essential building block for almost all of modern technology. It really makes you stop and wonder, doesn't it? What other simple, elegant solutions like this are out there, quietly shaping the world all around us?